This is the lecture video for Chapter 9, Periodic Properties of the Elements. We're going to take a look at the fourth and final quantum number, magnetic spin. We're going to use that to draw out orbital diagrams and electron configurations. And from there, we're going to understand the different trends in the periodic table. For those of you that have taken biology already, you should know about the sodium-potassium pump that's found in cell membranes of animal cells. So 3 sodium ions are pumped out of the cell, while 2 potassium ions are pumped into the cell. Now, how can the pump differentiate between the 2 ions so that the right number of ions are pumped in and out? Well, just take a look at the ion size of the sodium ion and that of the potassium ion. The potassium is much bigger than sodium, and that's one of the periodic trends that we'll take a look at: ion size and even atom size. Dmitri Mendeleev is the one who arranged the elements the way that we see them today. When he ordered those elements by increasing atomic mass, he saw that certain patterns occurred periodically. This is why it's called the periodic table of elements. So in this chapter, and even in the next chapter, I highly suggest that you have a physical copy of the periodic table. You'll be referencing it many times throughout this video, so you'll understand the concepts better if you have a physical copy in front of you and you're actively taking notes on that periodic table. That's why there are families in the periodic table, like the noble gases, halogens, alkali metals. All the elements in those columns, in those families, show very similar properties. Also, in his lifetime, not all the elements were discovered. So in places where elements were missing in the periodic table, Dmitri Mendeleev would predict the properties, physical and chemical, for those missing elements. These are 2 elements that he predicted, gallium and germanium. He was able to predict their atomic masses, densities, and even their chemical formulas when they bond with oxygen and chlorine. There have been talks of redesigning the periodic table. So here in this design, the lanthanides and actinides are actually inserted into the main part of the periodic table. Here's a totally different design to show the continuity of the elements instead of breaking them up into different parts. Most likely, we won't see any changes to the periodic table anytime soon. So we'll just keep using the table that we've been using for years, the one that's more aesthetically pleasing and can fit on one page. The periodic table is great, but it doesn't explain why we see those patterns in the families. So we have to continue on with our understanding of quantum mechanics so we know why those trends and the properties exist. In the previous chapter, we took a look at the first 3 quantum numbers, N, L, and ML. Those 3 together would describe an orbital that's in an atom. Now we're going to put those 3 numbers together to write out electron configurations. So we'll take the easiest example, hydrogen. If you take a look in your periodic table, you'll know that hydrogen would have 1 electron because it has 1 proton, so those different charges need to balance out in a neutral atom. The way that we write out the electron configuration is by using N and L. So this big one here, that represents N, which is the energy level. And the S, as you know from the previous chapter, S represents the L quantum number. This superscript 1 tells you how many electrons are in this particular orbital. So again, hydrogen only has one electron. So we would read this electron configuration as 1s1. We know that N, L, and Ml come from the Schrödinger equation, but that only works with hydrogen. What happens when we look at helium, lithium, and other elements that have more than one electron? There's going to be electron-electron interactions, so there's more variables there. And because of those interactions, we're going to see something called electron spin, and we're also going to see the splitting of sublevels. The whole idea of electron spin came from the Stern-Gerlach experiment. Here, the experiment showed that electrons actually spin on their axes. So when that happens, when charged particles spin, they generate their own magnetic field. So when this singular beam of silver atoms were sent through a magnetic field, some of the atoms were deflected upward and some were deflected downward. When we're talking about electron spin in terms of quantum mechanics, we're talking about our last and final quantum number, ms. Again, this is not part of the Schrödinger equation. This came from the Stern-Gerlach experiment. And here we show that the orientation of the spin is quantized. So there are two specific values that we're going to assign to ms. And we have to see if the electron is spinning upward or if it's spinning downward. We draw arrows pointing either upward or downward to represent electrons. If an arrow is pointed upward, then we're going to say that it has an ms value of positive 1/2. If it's pointed downward, then the value is negative 1/2. Here's our orbital diagram for hydrogen. Again, it only has one electron. When you need to draw just one electron in an orbital, you must draw the arrow pointing upward. That's the convention that we have to follow. If you need to draw another electron, a second electron in this orbital, then that arrow needs to be pointed downward. Okay, so the spins would have to cancel out if you're adding a second electron into this orbital. Now, let's put everything together in terms of our 4 quantum numbers. Pause the video and please figure out what the 4 quantum numbers are that would describe this orbital with the electron inside it. And when you're ready for the answer, click play. Okay, so for our n, we need to take a look at the name of the orbital. So the name of the orbital is 1s. This 1 that's depicted here, that is our energy level, which is represented by n. So our quantum number for n is 1. L is represented by s. That's our letter designation. And the number value for s is 0. So here, L is equal to 0. ML is based on our L value. If you forgot from the previous chapter, our possible ML values range from negative L to positive L. all the integers in between, including 0. Well, because our L value is 0, our ML value must also be 0. And then finally for MS, we just have to take a look at the orientation of our arrow. It's pointed upward. So our MS value is positive 1/2. As we're writing out electron configurations and drawing out orbital diagrams, we have to follow several rules. So here's our first rule, Pauli exclusion principle. It says that no two electrons in an atom can have the same set of 4 quantum numbers. So if we go back to our hydrogen example in the previous slide, we cannot have 2 arrows pointed upward, because then our 2 sets of quantum numbers to describe those electrons, they would be the same. We cannot have that. Our second arrow would need to be pointed down so that we can have 2 different sets of quantum numbers in an atom. If you remember how many orbitals there are in a subshell, then you'll know the maximum number of electrons that can be in a subshell. So for any of the S subshells, there's only 1 orbital, so they can only hold a max of 2 electrons. With the P subshell, we have 3 P orbitals, so 6 electrons. Now let's take a look at helium that has 2 electrons. Both of these electrons are still going to be in the 1s orbital, but they have to have opposite spins. Here you can see in the orbital diagram, one arrow is pointed up, the other one is pointed down. And because of that, we have 2 different sets of quantum numbers. Yeah, you can see that N, L, and ML are the same for both electrons, but if you look at them as a set, they are different because of the different MS values. I'll also notice the superscripts in the electron configuration. Here we have 1s2, so that 2 represents the 2 electrons found in the 1s orbital. When we take a look at the energy levels in hydrogen, all the sublevels in each energy level would have the same energy. They are called degenerate. But when we go past hydrogen, the different electron interactions would cause those sublevels to have different energies, or they would be splitting within an energy level. So because of that, we're going to see the s orbitals having a lower energy compared to p. And then p would have a lower energy level compared to d, which would have a lower energy level compared to f. This is how orbitals would compare in a hydrogen atom. You can see that the 2s orbital is at the same energy level as the 2p orbitals. So these 4 orbitals in n equals 2 are degenerate. They have the same energy. But now when we look at multi-electron atoms, those orbitals within an energy level are now split. So take a look at our orbitals in n equals 2. They are not degenerate anymore. 2s is at a lower energy compared to the 3 2p orbitals. But if you take a look at this subshell together as a whole, these 3 orbitals are degenerate. These 5 3d orbitals are degenerate, but they are not at the same energy level as the 3p and the 3s. So you see how they're all split up, all of these orbitals? You're going to have to know the order of these orbitals going from lowest energy to highest energy. There are two different ways for you to memorize this order, so don't worry if this looks like a jumbled mess. There is a method in memorizing this order. We're going to take a look at the 3 reasons why the subshells split up within a given energy level. Coulombs Law, shielding, and then electron penetration. Here's Coulombs Law. You need to understand this equation. You're not actually going to use it to solve for anything. So here we have energy equals to some kind of constant times the charge of one particle times the charge of a second particle divided by the distance between those 2 particles. Okay, so let's think back to classical physics. If you have 2 particles that have the same charge, they're going to repel. They want to be far away from each other. So if we take those 2 charges and we put them really close together, you need a lot of energy to hold them very close together like that. The potential energy there would increase. Now think back to chapter 7. If a system has a lot of potential energy, that system is considered unstable. So holding these 2 positive charges very close together is very unstable. They want to be far apart. They're going to repel. And in doing so, the potential energy is going to decrease. If you lower the potential energy of a system, it becomes more stable. These 2 similarly charged particles are more stable. They're happier as they get further and further apart. If you have a positive charge and a negative charge, they're going to be attracted to each other. So a very stable system here is if they are close together. Again, when they're close together, they are more stable, so the potential energy is going to decrease. Or in other words, the potential energy will become more negative. Another thing that you have to take a look here is the strength of the charges. So if you have a particle that has a +2 charge, then it's going to have a larger magnitude in energy compared to a 1+ charge. So for this equation, you need to understand that energy is directly proportional to the magnitude of the charges and inversely proportional to the distance between those charges. Here's our first question. Using Coulombs law, what happens to the potential energy of 2 oppositely charged particles as they get closer together? So pause the video, think this through, and when you're ready for the answer, click play. The answer here is A. Their potential energy decreases. Another way of saying it is the potential energy becomes more negative. Okay, so think back to the last 2 slides. You have a positive charge and a negative charge. They want to get close together. They are attracted to each other. They're moving to a more stable situation. So remember, as a system becomes more stable, the potential energy of that system decreases. If we look at an atom that's not hydrogen, all those electrons in that atom are going to experience repulsion and attraction at the same time. Electrons are negatively charged, so they're going to feel repulsion from other electrons. And they're also going to feel attraction towards the nucleus because of the positively charged protons in the nucleus. So for these electrons, they might not experience the full positive charge in the nucleus. Some of those electrons are going to shield other electrons from the nucleus. So we need to understand what's called effective nuclear charge. An electron is going to feel parts of that positive charge from the nucleus. Here's our equation for effective nuclear charge. Some people call it Z effective or ZF. They all mean the same thing. The Z stands for the number of protons in that atom, and S is the number of core electrons, or electrons in the lower energy levels. You don't have to worry about the effect that electrons have with each other in the same energy level, because they all contribute the same way, and the contribution is so small that it doesn't have to be part of the calculation. You just have to worry about the number of electrons in the lower energy levels. Here we have a lithium atom. There's a +3 charge in the nucleus. That means that there are 3 protons, so we're looking at lithium. There are 2 electrons in the lower energy level and 1 electron further out from the nucleus. So this electron here only experiences a +1 charge. When we use the Z effective equation, our Z is 3, our S is 2 because of these 2 core electrons, these 2 electrons in the lower energy level. So 3 minus 2 is +1. Our 2 electrons are shielding this outer electron from the +3 charge. When we talk about electron penetration, we're looking at 1 outer electron that's breaking through the cloud of inner electrons. So now that outer electron is going to have a stronger attraction for the nucleus. We're taking a look at lithium again with the 3 protons in the nucleus and 2 core electrons. This third electron was able to penetrate through the cloud of inner electrons. So now it experiences the full +3 charge, and it has a strong attraction to the nucleus. To understand penetration better, we're going to have to go back to the radial probabilities, probability density graphs, and nodes. So here we can see that for the 2s and 3s orbitals, there are nodes within those orbitals. Now, if you forgot from the previous chapter, a node is where nothing occurs. If you were going to give it a value, it would be 0. So here with electron orbitals, when you see a node, then no electron would occur in that space. Let's take a look at the radial probabilities of the 1s, 2p, and 2s orbitals so that we can understand penetration and shielding better. Now, the 1s orbital is very close to the nucleus. We could say that it tapers off a bit at around 120 picometers. So that's where we're going to draw our core electron shield. So any electrons found between 0 and 120 picometers, they're going to experience a great attractive force to the nucleus. Now let's take a look at the 2p radial probability. We can see that most likely an electron would be found beyond 120 picometers. With 2s, we could say the same thing. However, there is a small hump of the 2s orbital. There's a small hump that occurs between 0 and 120 picometers. This tells us that those 2s electrons can penetrate through the core electron shield. And so they would also experience a great attractive force to the nucleus. Another thing that we're going to say is that they are less shielded. These electrons in the 2p orbital, they cannot penetrate through the core electron shield. So those electrons, these 2p electrons, are considered to be more shielded, and they would feel more repulsion because you have two negatively charged particles coming together. They're going to experience repulsion. Even when we move up to n equals 3, these subshells, 3s, 3p, and 3d, they're also not in the same energy level. So here, let's just say that this is where our core electron shield is located. The 3p and 3s orbitals can penetrate through this shield. So with all this electron penetration and shielding, the sub-level splitting becomes more apparent as we move higher in n values. So when we reach the fourth and fifth principal levels, we can actually see that the 3d orbital is higher in energy compared to 4s. So when we look beyond 4s, the separations between the different energy levels get smaller and smaller. And that's what we see here. After 3p, we would think 3d would come next, but it's actually 4s. And as we move higher and higher in energy, we see that the distance between these levels, these energy levels, becomes smaller and smaller. Now let's check for understanding. You're going to pause the video, read through these statements, and pick which one is true. When you're ready for the answer, click play. The answer here is letter C. So let's break this down a little bit at a time. So we have an orbital that penetrates into the region occupied by core electrons. Okay, we're also saying that it's less shielded from nuclear charge than an orbital that does not penetrate. Okay, that should make sense because if you think back to our diagram with our core electron shield, if we have electrons that penetrate that shield, that break through that shield, then those electrons are less shielded. Now that same orbital would have lower energy. That would also make sense because the nucleus is positively charged, the electron is negatively charged. If that breaks through the core electron shield, well, now it's much closer to the nucleus than it was before. If we have two oppositely charged particles coming together, that lowers the potential energy in that system. Those charged particles want to come together because that makes it more stable. With all the electron configurations that we have to write out and orbital diagrams that we have to draw, we need to follow some rules. You already know the Pauli exclusion principle, and we're going to review that here. This one is the Aufbau principle, and Aufbau means building up in German. So what that means here is that when we're adding electrons to orbitals, we have to start with the one that has the lowest energy and then work our way up. So generally speaking, we're going to follow the letter designations for L. So that's S, P, D, and F being the highest level energy. But specifically, we're going to follow the orbital order of filling. Next, you need to know that some orbitals are degenerate, and that just means that they are at the same energy level. Pauli exclusion principle, you know, we can't have two electrons with the same set of quantum numbers in an atom. So that also means that in an orbital, we can have a maximum of two electrons, one pointed up and one pointed down. If we add a third one into that orbital, well, the third one can either be pointed up or down, and that's where we violate our Pauli exclusion principle. The last rule is Hund's rule. So for those orbitals that are degenerate, when we start filling them up, we have to fill them up singly first. Then we can start pairing up electrons. So now let's say we are looking at carbon that has 6 electrons, and we need to fill up this orbital diagram with the 6 electrons. Okay, so where are we going to put our first electron? We can't put it up here. We can't put it in 3p. We have to start with the lowest energy level orbital. So that's 1s. This is Aufbau principle. Okay, so our first electron needs to be an arrow pointed up. Where are you going to put the second electron? Again, we can't put it anywhere. Can't put it at 4s, can't put it at 2p. We have to finish off this lowest energy orbital, again with Aufbau. Now we have to draw the arrow pointed down. That is the Pauli exclusion principle. Now these two electrons have two different sets of quantum numbers. Okay, now where are we going to put the third electron? We now have to put it at 2s with an arrow pointed up, and then we got to finish it off with an arrow pointed down. Okay, so that's 4 electrons. We need to add 2 more. Our next set would be 2p. Now here are 3 degenerate orbitals. They're orbitals that have the same energy. So we're going to put 1 electron, again pointed up, in the leftmost orbital. Where are we going to put our last one? It has to be in another orbital. This is Hund's rule. For degenerate orbitals, you have to fill them up singly with electrons first. Okay, so this is carbon. What happens if we need to do the same thing for oxygen, which has 8 electrons? Well, we're filling it up the same way with Aufbau, using Aufbau's principle and the Pauli exclusion principle. Okay, so now where are we going to put the 7th electron? In the other 2p orbital. Where will we put the 8th? In the first one with the arrow pointed down. Here we have some elements with their electron configurations and orbital diagrams. Note the superscripts for all these electron configurations. They add up to the number of electrons that are found in those atoms. This is one way of memorizing the order of filling for the different subshells. You'd have to write out these orbital names in this particular orientation, and then you have to draw arrows diagonally, starting from the upper right-hand corner and going down to the lower left. You do this so that you could read it in the particular order that's needed. So we'll go 1s, then 2s, then 2p and 3s, 3p, 4s, 3d, 4p, 5s. So that's the whole idea here. I personally don't like this method because I know I will just mess it up. If this works out for you, then go ahead and use this method. Having the periodic table handy will help you use this second method that I like to use. We're actually going to break up the periodic table into 4 different blocks. We're also going to take note of the period number or the row number so that we understand the principal energy level for these electrons, or in other words, the N value. Also, we have to take note of the main group elements, because the number label for those columns would tell us the number of valence electrons there are for that atom. Here's our periodic table. We're going to have to do a few things to it just so we can understand how to write out the electron configurations. So we're going to take helium and bring it over to the left-hand side right next to hydrogen. Also, we're going to draw a line, just like a dividing line or a zigzag, here between Ca and Sc all the way down. We're going to draw another line between Zn and Ga all the way down. Also, take note of the numbered rows, the numbered periods, because they will tell you the N values, the energy level values. And here we are with our 4 different blocks. The first 2 columns represent S. The last 6 columns represent P. The 10 middle columns represent D. And the bottom ones here with the 14 columns represent F. Now this should make sense if you know how many orbitals there are in these subshells. So for S, let's go back to S. The S subshell has 1 orbital. Now think, how many electrons can we add to that 1 orbital? What is the maximum number? It's 2 electrons. Well, that's why we have 2 columns here that make up the S block. Now let's go over to P. There are 3 orbitals in the P subshell. So what is the maximum number of electrons that can be in the P subshell? The answer is 6. So that's why we have 6 columns. Same thing goes for the 10 columns for D and 14 for F. Okay, so again, let's take helium, bring it over to the left-hand side next to hydrogen. Here they noted where chlorine is, Cl. We see that it is in the 3rd column, third row, 5th column in the P block. So that's why they have written here 3p5. This is our destination. Where is our starting point? Over here at hydrogen with 1s1. This is going to be our roadmap. Our periodic table is our roadmap from our starting point to our destination. Now you have to remember Aufbau principle. We have to start with the lowest energy orbital and work our way up. Again, 3p5 is our destination. We have to go through the periodic table until we reach our destination. When we reach the end of a block in a row, then we have to write that orbital name and the maximum number of electrons in that subshell. Okay, so let's start off here just for practice. We need to end at chlorine, 3p5, and we're going to write out the electron configuration. So we're starting off at 1s1. We keep going. We're at the end of the block. Again, we're pretending that helium is right here. So we're going to write down 1s2. Now we're moving on to the next row. We're going to keep going. We're at the end of the block. So we're going to write 2s2 because we're in the second row. Now let's keep going. There's no D's here. We're in the P region. Okay, we're going to keep going until we reach the end of this block. This is now 2p6. Let's go to the next row. At the end of the block, we write 3s2. We're going to keep going, going, going. There are no D's here. Now we're at the P region again, and we reach our destination, and we write 3p5. So the electron configuration for chlorine is 1s2, 2s2, 2p6, 3s2, and 3p5. This picture here shows you only parts of the electron configurations for these elements. Just like it looks like just the last two orbitals of these elements, but it'll show you how you just follow through. You just follow through, going from left to right, top to bottom, when you're writing out these orbitals, when you're writing out these electron configurations. One thing that you have to note here is for n equals 4, we are at 4s in the s block, but once we hit the d block, we're not at 4d, we're actually at 3d. So when you're writing out configurations and you hit the d block, you're actually writing n-1. So for S, that's just regular n. You write down whatever period number you're at. But for D, you're writing n-1. So we're in the fourth period. n-1 is 4 minus 1, so that's why we have 3D in this row. And once you hit the P block, we're back at 4. Okay, now going into the F block, take a look at what number F is here. It's actually 4F, not 6F, not 5F, it's actually 4F. So with the F block, you're actually thinking of n-2. When you're done with this row, you're going back to the D block. That'll be 5D. And then moving further into the P block, you're at 6P. This picture highlights the main group elements. So you could see the column names labeled 1A to 8A. And again, that'll tell you how many valence electrons, how many outer electrons there are for each of those elements in those columns. So again, looking at chlorine, okay, we're counting 7 here. 2 plus 5 equals 7. We're in the 7th column. Same thing for F. Same superscripts, it's just different n values. Now draw out the orbital diagram for sulfur and figure out how many unpaired electrons there are. So please pause the video, look at your periodic table to see how many electrons there are. Draw out your orbital diagram, and when you're ready for the answer, click play. Okay, so here's the diagram for sulfur. Again, note how many orbitals there are in each subshell. So all the S subshells have 1 orbital. All the P subshells have 3 orbitals. Each orbital can hold a maximum number of 2 electrons. Here with the P subshell, we can see Hund's rule. The electrons are filled up singly first, and then with the 4th electron, the final electron is going to be pointed down. You'll be seeing this phrase a lot in the textbook, ground state. What that means is no electrons were excited to a higher energy level. So this goes back to the previous chapter, where electrons could absorb photons and then be excited to a higher energy level. And then when they relax, they would release some radiation as they go down from a high level to a lower energy level. So when you see electron configuration in the ground state, just write out the electron configuration as you've done before, following the order of filling and the alphabet principle. That's all you have to do. Okay, so here we have krypton. It's over here, number 36. So we need to have 36 electrons. Always write out the number of electrons that you need in your configuration. Okay, so again, we're going to bring helium over to the left-hand side. Krypton is our destination. Okay, so that is, we're in the 4th row, so that is 4p6. That's going to be the last orbital that we're going to write in our configuration. Remember, whenever we reach the end of a block, wherever we are, we have to write down the orbital name and the maximum number of electrons in that subshell. So as we keep going, from left to right, top to bottom, we have this configuration. Again, when we reach the 4th period, after we're done with 4s, we're in the D block, we have to write down 3d. And once we're done there, we are back at 4, and here's our destination, 4p6. There is an easier way to write out very long configurations, and that's using a noble gas in brackets. So here in this example, we have rubidium. Okay, it's in the first column, number 37. So that means we're working with 37 electrons. This is the electron configuration, the full electron configuration for Rb. Now, the shortcut tells you to go back to the previous row. Go back to the previous row and write down the noble gas in brackets. Okay, so that takes care of 1s2 all the way to 4p6. That was our previous example. Okay, when we do that, then all we have to do is write 5s1. And this is our electron configuration here, our little shortcut for Rb. Krypton in brackets, 5s1. From here, you should be able to figure out the 4 quantum numbers. It depends on how specific the question is. So if we take a look at rubidium and you're asked to write out the 4 quantum numbers for the electron in 5s1, you should be able to give all 4 numbers. So the 5, again, represents N. S is our L value. So when we see S, we're going to think 0 for L. ML is based on L. So remembering the rule there, we can only have 0 as our value for ML. And the positive 1/2, we know that if there's one electron in an orbital, that's an arrow pointing up. So we have our definite answers for our 4 quantum numbers when we're asked about 5s1. Now, if we're asked about an electron in the 2p subshell, well, that's where things can get a little bit more general. Now, for sure, N is equal to 2 and L is equal to 1. But because they did not specify the orbital, we have to write out all 3 values for ML. And again, they did not specify which electron in the orbital. We don't know if the arrow is pointed up or pointed down, so we have to give both values for MS. Let's test for understanding. So here we have 4 choices. We need to know what the 4 quantum numbers are for each of the 2 electrons found in a 4s orbital. So pause the video, look through all the choices very carefully, and then press play when you're ready for the answer. Our answer here is letter B. That should make sense because these 2 sets of quantum numbers are different, so we're not violating the Pauli exclusion principle. All these, the first 3 quantum numbers in both sets make sense. Let's take a look at A. This one is no good because both sets are the same thing, so this violates the Pauli exclusion principle. Same thing for letter D. Letter C is incorrect because the N value is incorrect. So our answer is B. Here we want you to practice writing out the electron configurations for each element. So don't just write out the long version, also write out the noble gas shortcut. So please pause the video, look at your periodic table, and practice writing out both versions of the electron configurations. When you're ready for the answers, click play. So here we are with the long version and the noble gas shortcut. Just take a look at bromine for a moment. You see that up until 3p6, we have argon. Okay, so after argon, you have to continue with the rest of the configuration. You can't just end at 4p5. You wouldn't even have enough electrons when you count everything. That also violates the Aufbau principle because you missed 2 lower subshells. Okay, so when you write the noble gas in brackets, you have to continue with the rest of the configuration. Try these out. Write the electron configurations for selenium, bismuth, and iodine, but write the noble gas shortcuts. Write the noble gas shortcut for these 3. So please pause the video to do all that. When you're ready for the answers, click play. Okay, here we go. Here we go. Don't forget to completely write out the rest of the configuration after you write the noble gas in brackets. A lot of students forget the ones in the middle and just write their destination. And again, here I'd like to point out for bismuth, you'll see that some of the electrons are in the f orbital or f subshell. So don't forget how to write those out in terms of N values. You've been hearing me say valence electrons and core electrons. Those are basically just the outer electrons and inner electrons. But we have to be a little bit more specific here. So for you to figure out which ones are core electrons, you need to see which energy levels are completely filled with electrons. So if we take a look at 1s, n equals 1. We only have one orbital, and it can only be filled up with 2 electrons. So our 1s2, those 2 electrons in that orbital, are considered core electrons. Now let's move on to n equals 2. So that's our 2s and 2p. These 2 subshells are also completely filled with 2 electrons for 2s and 6 electrons for 2p. So these 8 electrons are also considered core electrons. Now let's move to n equals 3. Here, the 3s orbital is completely filled up, but the 3p subshell is not completely filled. So because of that, these 4 electrons are considered valence electrons. All of the n equals 3 orbitals are not completely filled. Now let's see what you all remember. Without writing an electron configuration, determine the number of valence electrons in nitrogen. Please pause. Hopefully you remember the trick. When you're ready for the answer, click play. The answer is 5 valence electrons for nitrogen. If you take a look at the periodic table, you'll see that nitrogen is a main group element. So you could just take a look at the group number and you'll see how many valence electrons those elements would have in that family. Now try figuring out how many valence electrons and core electrons there are in GE. You have to write out the electron configuration first, so please pause the video to do that. And when you're ready for the answer, click play. Okay, so here's the electron configuration. We see that here in this case, all of the orbitals in n equals 3 are completely filled with electrons. So they are going to be counted as core electrons. The 4s2 and 4p2, the electrons found in those subshells are considered valence. So don't let the order fool you. Okay? Yes, 3d is written after 4s, but it's part of a lower energy level. Okay, please do the same thing for phosphorus. Write out the electron configuration and figure out which ones are valence and which ones are core. Pause the video to do that, and when you're ready for the answer, click play. Okay, here's the electron configuration. Our valence electrons occur in 3s and 3p. And this should make sense with 5 valence electrons because phosphorus is in the 5th column. All we were looking at so far were elements in the main groups. Now we have to take a look at the transition metals and see how those electron configurations look. So you could see for the most part, they look pretty normal. We have 4s2, 3d1. We keep increasing 3d2. Okay, but okay, now look at chromium, Cr. This doesn't make any sense. Why is it now 4s1 and then 3d5? Yeah, now there are 6 electrons here, 5 electrons here, but why is this 4s1? And then when we move over to manganese, we're back to 4s2, and now this is 3d5. It stayed the same as before. What's happening here? It's all because of the sublevel splitting. Remember that as we move higher and higher in energy, the energy differences between those high energy levels are getting smaller and smaller. So that's why 4s is at lower energy compared to 3d. So for these transition metals, you'll see that there's going to be some irregular electron configurations. For these 5 elements, we're showing you the configurations that are expected. But found experimentally, we actually see these electron configurations. So I already pointed out Cr. We would think that it'll be 4s2, 3d4, but in actuality, it's 4s1, 3d5. You must memorize these 5 irregular electron configurations. We already know that the elements are arranged by increasing atomic number, and also they're grouped by their similar properties. But now, since we know more about electron configuration, we could take a look at how they're similar in that way. So with alkaline earth metals, we see that they all have 2 valence electrons, and they all occur in the s orbital. With halogens, there are 7. With noble gases, there are 8. With the noble gases, you might have heard this phrase before, complete octet. That just means that there are 8 valence electrons in the outer shell. And this is true for the noble gases, except for helium, so we actually say that it has a complete duet. Now, why are they called noble gases? It's because they don't really react with anything else. And why is that? It's because having 8 valence electrons makes those atoms extremely stable. That's why they don't want to react with anything else. When ions are being formed, and specifically from the main group elements, those ions will actually obtain the electron configuration of a noble gas. So looking at alkali metals, they all have 1 valence electron. When they lose that electron, they'd have the same configuration as the noble gas from the previous row, and thus make those ions extremely stable. With halogens, we know that there are 7 valence electrons. So in order to obtain a noble gas electron configuration, all these halogens need to gain an electron. So when these elements form ions, they'd have a charge of -1. The other main group elements form ions in the same pattern. Okay, they gain and lose electrons just so they can obtain the configuration of the nearest noble gas. So if you don't understand that concept already, I highly suggest you memorize these predictable charges. Okay, if you know how many valence electrons there are, then you know how many electrons need to be lost or gained so that those elements can have a complete octet. Okay, so for the group 1 metals, they all have one valence electron, so they have to lose that valence electron in order to have a complete octet. So that's why all their charges are +1. Same thing with the second group. They have 2 valence electrons, so they need to lose both of them to obtain a complete octet. The ones that you probably haven't really seen before would be those in 3A and 5A. So again, I highly suggest you memorize these predictable charges if you're not used to seeing them already. Let's test your understanding. So we have a main group element that has an outer electron configuration of Ns2, Np4. What charge is likely for an ion of this element? So pause the video, think it through, and when you're ready for the answer, press play. Okay, the answer here is -2. So let's take a look at our periodic table here. Okay, so Ns2, Np2, and Np4. We're just going to pick whatever period. Let's just pick period 2. Okay, Ns2, we're going past it. We need to be in the P region. So it says P4. So this is P1, 2, 3, 4. That's S2 minus. Okay. Well, let's try another one. Let's try the 4th row. Okay, so we're at Ns2. We'll just keep going, going, going. We need to be in the P region. Here we go. Te2 minus. Okay, so with this general configuration, all you really had to do was count the superscripts, and that'll tell you what column we were looking at. Now let's try writing out electron configurations of ions in their ground state. So again, none of these electrons were excited to a higher state. You just write them normally. Okay, if one of these electrons were in a higher state, then, for example, this would be instead of 3p4, it might be 3p3 and then 5s1. So it could have the same number of electrons. It's just that one of them was excited to a higher energy level. Okay, we don't have that here. Everything is, all the electrons are in their regular states, in their ground states. Okay, so with sulfur, we already saw that it would gain 2 electrons so that it can have a noble gas configuration. Where are we going to put those 2 electrons? There's room in the 3p subshell, so that's where we're going to put our 2 electrons. Now looking at the cations. Mg would need to lose 2 electrons so it could have a noble gas configuration, a complete octet. Which electrons are going to be lost? It'll be the 3s2. Those electrons would be removed. Okay, so here, whichever electrons are in the highest energy level, they're the ones that are going to be lost. Now we're going to take a look at periodic trends. And the first trend that we're going to see is atomic radius for the main group elements. Now there are different definitions for atomic radius. It all depends on what type of atom we're looking at. Is it being bonded with something, or is it part of a metal? Here specifically, we're going to take a look at atomic radius, which is just an average based on elements and compounds where those atoms are found. Here we could see in this picture that the atomic radius decreases across the period from left to right. So let's take a look at lithium. It's in the second period. Just generally speaking, as we move from left to right, going towards neon, the atomic radius is decreasing. Now, why is that? That's because effective nuclear charge is increasing going from left to right. So don't forget that formula. Z effective equals the number of protons minus the number of core electrons. As we're moving from left to right, the number of protons are increasing, but the number of core electrons stay the same. That's why Z effective increases from left to right. So what does Z effective have to do with atomic radius? Well, remember, Z effective, you could think of it as the nuclear pull on those valence electrons. If Z effective is strong, then it's really going to pull those valence electrons close to the nucleus. And if it does that, then the atomic radius will decrease. So if there is a strong attraction for the valence electrons, the distance between the nucleus and those valence electrons are going to be small. Again, because of Z effective. Let's review shielding and effective nuclear charge. Here we have a lithium atom. It's got 3 protons in the nucleus, 2 core electrons, and 1 outer valence electron. These core electrons would experience the full +3 charge. But this outer valence electron would only experience a charge of +1. Why is that? The core electrons, the 2 core electrons, are providing a shield to protect the valence electron from the positive charge. Now, as we move from left to right in the periodic table, the number of protons would increase. Okay? If we stay in the same row, then the number of core electrons would stay the same. So what's going to happen to Z effective as the number of protons increase, but the core electrons stay the same? Z effective would increase. And so the valence electron would be pulled closer and closer to the nucleus. And when that happens, the atomic radius would decrease. Just to review a little bit more, when we have a multi-electron system, the outer electrons are going to be repelled by the inner electrons, but they're also going to be attracted to the nucleus. Also, with the outer electrons, they're not going to do any shielding. They're not going to shield each other from the positive charge. Only the inner electrons will do that. So that's why our Z effective formula is just simply number of protons minus the number of inner electrons. Now let's test your understanding. Which electrons experience the greatest effective nuclear charge? The ones in magnesium, the ones in aluminum, or the ones in sulfur? So pause the video, figure this out, and when you're ready for the answer, click play. The answer is letter C, the valence electrons that are found in sulfur. Here you need to use the Z effective equation. You should also know, hopefully you looked at the periodic table, that these 3 elements occur in the same period. So moving from left to right, the number of protons are increasing, but the number of core electrons stay the same. So look what happens to the Z effective. As we move more and more towards the right, Z effective is increasing. Well, don't forget about the atomic radius trend moving from left to right. Sulfur would have the smallest radius. Now let's take a look at what happens to the radius as we go down a column. Here we could see the alkali metals. So when we start from the top and move our way down, we see that the atomic radius is increasing. The same can be said for the noble gases. Going from top to bottom, the radius is increasing. And that's because the valence shell is moving farther and farther away from the nucleus as we go down the column. If you remember how the 1s orbital, 2s, and 3s orbitals look like, then you'll understand why the atomic radius increases when we move down the column. Okay, as we move down, the value of n increases. Now, think about 1s, 2s, and 3s. They're all spherical. As we increase n, the number of nodes also increase. Not only that, the size of those orbitals increase as n increases. So with valence electrons in the 3s orbital, they are much farther away from the nucleus compared to valence electrons in the 1s orbital. Let's take a look at transition metals now. If we just look at one column and go down that column, the atomic radius is going to increase. Going from left to right, however, the size of the atom is going to be pretty much the same. The radius isn't going to change too much, and that's because the Z effective is about the same going from left to right. As part of your studying, I highly suggest you have a physical periodic table so that you could write out all of these trends on that one periodic table, and that'll be your reference. So here with atomic radius, you could see that the radius is increasing when we go down the column, and it's decreasing when we go from left to right. So that's true with the main group elements. But take a look at the transition metals going from left to right. Yeah, we could see that it is decreasing, but then at some point it starts to increase again. So with transition metals, just worry that going down a column, the radius increases. Okay, so let's see if you understand the atomic radius trend. Here we have 4 pairs. You need to choose the larger atom if it's possible. So pause the video, take a look at your notes, your periodic table, make your choices, and then press play when you're ready for the answers. Okay, so for part A, the nitrogen atoms are larger. So when we're doing this, we're going to start off with nitrogen and then move up, down, left or right so that we get to fluorine. So here all we have to do is just move towards the right. And we know that the trend for atomic radius is decreasing as we move from left to right. So the N atoms are larger. For part B, GE atoms are larger. So we'll start off with carbon and then go down the column. And we know the trend. As we go down the column, the atomic radius increases. So germanium atoms are larger. Al atoms are larger in part C. So we'll start off with nitrogen. We're going to go down, so that's increasing the radius. And then we're going to move to the left, which also increases the radius. And that's why Al is our answer here. Now let's take a look at Al and Ge. We start off with Al and we move to the right. That decreases the atomic radius. Now we're going to go down the column. That increases the atomic radius. So because we have that counter effect, we can't really tell which one is actually the larger one. So for part D, we just don't know. Try this one out. Again, you're choosing the larger atom in the pair. So please pause this. Use the periodic table that's given to you to figure out which one's larger. When you're ready for the answers, click play. Now you have 5 elements that you have to arrange in decreasing radius. So that means the last element that you're going to write in your list would have the smallest radius. Please pause this to reason it out, and when you're ready for the answer, click play. By now, we should be comfortable in writing out electron configurations for cations in the main group. Here we have aluminum. We know that it forms a +3 cation, so we need to remove 3 electrons from the 3s and 3p. So we end up with this configuration and this orbital diagram. With transition metal cations, it could be a little bit tricky. And that's because of the subshell splitting. We have to take a very close look at the electron configuration and determine which electrons need to be removed. Let's take a look at iron, which is a transition metal. Here we have the electron configuration for it. If we need to remove 2 electrons so that we could form Fe2+, we have to remove the 4s electrons first. Yes, they're written first, then comes 3d, but 4s is at a higher energy level. It's at a higher principal energy level, because n equals 4. It's higher than n equals 3. So we have to remove those 2 electrons first. If we need to remove another electron, because iron can form +3 cations, then that's when we can remove an electron from 3d. And here's the orbital diagram for that, for Fe3+. We could see that there are no electrons in the 4s orbital, and that all of the electrons in 3d are unpaired. This leads into the magnetic properties of atoms and ions. So we'd have to look back at the Stirling-Gerlach experiment with the silver atoms being sent through a magnetic field. Some of those atoms were deflected upward, others were deflected downward. This showed that the electrons spin on their own axes and they generate their own magnetic fields. So when these atoms were sent through a different magnetic field, they were attracted to that field. And here's the electron configuration for silver. We see that it has one unpaired electron, so it exhibits paramagnetism. And this is why those atoms were either deflected upward or downward. With diamagnetism, all of the electrons are paired up, so there would be no magnetic field generated. And here's an example with zinc. All the electrons are paired up, including the valence electrons. Now you have to figure out which of these are diamagnetic and which are paramagnetic. You have to write out the electron configurations first and then draw the orbital diagrams for all of them. So please press pause, take the time to work all of this out by yourself, and when you're ready for the answer, click play. Okay, so here are the electron configurations. For the main group elements, they would all have a noble gas configuration. So for Al3+, really we should have neon in brackets. But that won't help us here in figuring out if it's diamagnetic or paramagnetic. So we needed to go a period further up so that we have helium in brackets and then the rest of the configuration. Okay, so here are two examples of the orbital diagrams. We have Al3+, and we could see that all of the electrons are paired up. We don't have to draw the electrons here because they would have to be paired up if we were going to move on, with Aufbau principle, if we move on with the rest of the orbitals. Now with Fe3+, we saw this earlier. There are no electrons in 4s, so we have to draw the electrons in 3D, and we see that they're all unpaired. So Fe3+ would be paramagnetic, Al3+ would be diamagnetic. You can't just go by the ion charges. You have to write out the configuration, and then you have to draw the diagrams to figure out if it's diamagnetic or paramagnetic. We'll look at ionic radius now, and we can see that it's very similar to atomic radius. As we go down the column, the ion size would increase for the same reasons. Now we have to take a look at cations and anions and how they compare to their neutral atoms. Cations are smaller than their atoms, anions are larger than their atoms. When comparing ions that have the same type of charge, we really have to look at things that are isoelectronic. And that just means that all those species would have the same electron configuration. So if we have something like that, here's an example. All four of these ions have 18 electrons. Which one is going to be the largest in the group? Well, that'll be S2-. The trend is the larger the negative charge, the larger the anion. Now looking at the positive charge. As the positive charge value increases, then the smaller the ionic radius. Again, this works if we have an isoelectronic series. This is a very nice picture showing cations compared to their neutral atoms. All the cations are smaller in size compared to their atoms. Also note, going down a column, the ionic radius is increasing. Also moving from left to right across the period, you could see that the atomic radius is decreasing. Now think of what happens when an atom becomes a cation. Electrons need to be removed from that outer shell. So if we take a look at sodium, it's got a valence electron, 3s1. To form a cation, we have to remove that 3s1 electron. So now what are our new valence electrons? 2s2 and 2p6. Now those valence electrons are going to get pulled closer to the nucleus because of the Z effective, and so that cation would have a smaller radius. We know the radius would increase as we move down a column because the N value would increase. And moving from left to right, the radius would decrease because the effective nuclear charge would increase moving from left to right. Looking at anions now, we see that they are larger compared to their neutral atoms. Also moving from left to right, we could see that the radius is decreasing. And going from top to bottom along a column, the radius is increasing, just like for atomic radius. Let's understand what's happening when an atom is becoming an anion. Electrons need to be added to that outer shell. So if we consider chlorine with 7 valence electrons, it needs to gain 1 more electron so it could have a complete octet. Now, what's going to happen there when we introduce 1 negatively charged electron to a bunch of negatively charged electrons? We're going to have repulsion. And because of that, the size of the anion is going to get larger. I could imagine those electrons needing a little bit more space to be happy as a negative Cl ion because of all that repulsion. And in the same way that we saw with the cations, moving down a column, moving down a group, the radius would increase. And then moving from left to right, the radius of the anions would get smaller because of the increasing effective nuclear charge. Now let's test for understanding. We see how the number of electrons and the number of protons affect the size of an atom or ion. However, we have not considered how the number of neutrons affect the size of an atom. Would you expect isotopes, for example, C12 and C13, to have different atomic radii? Please pause this to think through your answer choices, and when you're ready for the answer, click play. So the sizes of these two isotopes are going to be the same. The only difference is the number of neutrons. So C13 would have 1 more neutron than C12. Neutrons don't have any charge. Maybe the C13 would just be a little bit bigger, but I really don't think so. The size really depends on the number of electrons and the number of protons. Again, if we go down a column, then the orbitals will get larger and larger. If we move from left to right, the number of protons will increase, but the number of core electrons will stay the same. And because of that, the radius would decrease as we move from left to right. So let's see how well you do here. we have 6 pairs of ions and atoms, with the last pair being 2 ions. You need to choose the larger species from each pair. And then with the last part, part G, you're going to arrange those 3 species in decreasing radius. So the last species that you're going to write, that will have the smallest radius. So please pause the video, figure all this out, and when you're ready for the answers, click play. Okay, so for part A, the larger species would be S2-, because again, sulfur is gaining 2 electrons. There's going to be a lot of repulsion between those 2 newly added electrons and the 6 that were already there. So it's going to need more space. The radius is going to get bigger. For part B, the calcium atom is going to be the larger species. As 2 electrons are being taken away, an energy level disappears. So the ion becomes smaller. But because of the new valence electrons, the 8 electrons that are now the complete octet, because those electrons are much closer to the nucleus, they're going to get pulled even further closer to the nucleus. For part C, we have 2 isoelectronic species. And remember the rule there. The species that has the more negative charge is going to be the larger species. Part D is the same reasoning as part B. Part E has the same reasoning as part A. And F has the same reasoning as part C. Those are 2 isoelectronic species. With G, all 3 of these are isoelectronic. They have the same number of electrons. So we're going to use the same trend. The larger species is going to be the one that's most negative. The smallest species is the one that's going to be most positive. So that's why we have the order Cl-, Ar, and then Ca2+. Our next trend is ionization energy. That is the energy needed to remove 1 electron from an atom or ion. And now that's very specific. It's the minimum energy needed to remove 1 electron from an atom or ion. They have to be in the gaseous state. It is an endothermic process because energy is needed to remove that electron. And valence electrons are the easiest to remove. So let's take a look at these equations here. If, for example, we have calcium again. Calcium forms a 2+ ion, so 2 electrons are removed. The 2 electrons are not removed at the same time. They're removed one at a time. So pretend here we have Ca, calcium, in the gaseous state, and a certain amount of ionization energy is needed to remove 1 electron. So now we have Ca+. We need to remove a second electron. So we need a second ionization energy. Here again we have Ca+, or Ca1+. We need ionization energy again so that we have Ca2+ to remove that second electron. here, it's not going to be the same amount of energy as before. We're going to need more energy to remove that second electron. Why is that? Well, we're removing something negative from something that's already positive. So it'll be harder to remove that second electron. Before we get into the trends of ionization energy, we have to take a look at effective nuclear charge. We cannot escape from it again. So with a large effective nuclear charge, it's going to be harder to remove that particular valence electron. Again, the pull would be very strong. The nucleus is going to pull those valence electrons closer and closer to it as the Z effective increases. So, looking at ionization energy, it decreases going down the group because the atomic radius increases as you go down the group. So those valence electrons are far away from the nucleus. Now, as we move from left to right across the period, the ionization energy increases. And again, that's because of Z effective. That increases moving from left to right. Let's take a look at the second period. So lithium, going from left to right, generally speaking, the ionization energy increases. Okay, there's something weird going on here. Okay, it's decreasing and then increasing and decreasing again. So we'll take a look at this weird anomaly here later on. Okay, so that's moving from left to right. Going down a column, so let's take a look at the alkali metals. Going down a column, we can see that ionization energy decreases. And that's because of increasing atomic radius. Make sure you draw these trends in your periodic table with all your notes. Going down a column, the ionization energy decreases. Going from left to right, the ionization energy increases. If you need to draw out pictures to understand ionization energy better, then please do. So if you have a large atom, an atom with a very large radius, then the valence electrons in the outer shell would be far away from the nucleus. So the nucleus wouldn't have such a strong pull on those valence electrons. That means it'll be easier to remove those valence electrons from the atom. And because it's easier to remove, then less ionization energy is required to remove them. More energy would be needed to remove them if the radius gets smaller and smaller and smaller. Then the nucleus would have a stronger and stronger pull on those valence electrons. The same idea with Z effective can be seen as we move from left to right across the period. Because Z effective is increasing from left to right, then it'll be harder to remove an electron, a valence electron, from that atom. So that means ionization energy will be larger moving from left to right. Now let's pick out from each pair the one that has the higher first ionization energy. So please pause the video, look at your periodic table, reference the trends, and pick which one has the higher ionization energy. When you're ready for the answers, click play. Okay, so here for part A, S has a higher ionization energy. So let's start with Al. We're going to have to move to the right to get to S. Now moving from left to right, we know that ionization energy increases because Z effective increases. So our answer here is S. For part B, arsenic has a higher ionization energy than antimony. So we'll start off with As. We got to move down to antimony. And as we're moving down, the atomic radius is increasing. That means it's easier to remove a valence electron from the outer shell. So less ionization energy is needed for Sb. Our answer here is As. N is the one with the higher ionization energy. So that's where we'll start. We need to go down a column. So that'll decrease the ionization energy. And then we're going to move to the left, which also decreases the ionization energy. Now let's take a look at O and Cl. We'll start off with oxygen, and we're going to move to the right. So ionization energy would increase, and then we got to move down the column where ionization energy decreases. And because we have those counter trends, we can't say for sure, just based on the trends, which one has the higher ionization energy. Try out this set now. Again, pick out the higher first ionization energy if you can, using the periodic table. Pause the video to work it out, and when you're ready for the answers, click play. You're going to arrange these 5 elements based on decreasing first ionization energy. So the last element that you're going to write has the smallest first ionization energy. Please pause the video, use the periodic table to help you out, and when you're ready for the answer, click play. Earlier, we saw the exceptions in the first ionization energy trends. That picture with all the elements in specific periods, there were some parts where the ionization energy decreased a little bit and then increased again. So that was happening where 2A moved on to 3A and then 5A to 6A. So we're going to be taking a closer look at those pairs. So let's take a look at beryllium and boron. Beryllium has 2 valence electrons, and they're paired up. So it's going to be very difficult to break up this pair. This is very stable. So the first ionization energy here is going to be very large. Okay, a lot of energy is going to be needed to remove that 1 electron. Now let's take a look at boron with 3 valence electrons. It's very easy to remove this lone electron, okay, because its result will be a very stable situation. So this is where the first exception happens. Next, we have nitrogen and oxygen. If you take a look at nitrogen with its 5 valence electrons, we see that in the 2p subshell, all 3 electrons are in their own orbitals, and they're half-filled. It's a half-filled subshell. So this is also very stable. A lot of energy is going to be needed to break up this stable system. when we take a look at oxygen. It's going to be very easy to remove this one electron, the arrow that's pointed down, because look at the result. We would get a half-filled subshell, which again is stable, and we saw that with nitrogen. For the most part, what we saw were first ionization energies. Only one electron was being removed. Well, what happens when we need to remove a second electron or even a third electron? How would those ionization energies look? Well, for every electron that's being removed, more energy is needed to remove it. Now, let's take a look at this picture here. With sodium, we already know that it has one valence electron. So removing it would require a certain amount of energy. Now, if we need to remove a second electron in sodium, this is now Na+, and we're removing something negative from something that's already positive. That's going to require a whole lot of energy. So you see this huge jump here. This tells you that you're now removing a core electron. What you removed before was a valence electron. Now take a look at magnesium. That's found in the second column. It'll form a +2 cation. So let's take a look at the first ionization energy. We have 738. Removing the second electron would require more energy, and that's expected because we're removing a negatively charged electron from an ion that is positively charged. So of course, it'll take more energy to remove that second electron. Now, what happens when we want to remove a third electron? Look at this huge jump between the second and third ionization energies for magnesium. This tells you that the third electron is now a core electron that's being removed. The previous two were valence electrons. So whenever you see a very large increase in energy, you know that core electrons are now being removed. Here's another way of viewing successive ionization energies. Here on the left-hand side, I hid the elements that correspond to the sets of ionization energy values. I can tell you that the elements occur in the third row of the periodic table. If I point out this set of ionization energies, you should be able to tell me which element in the third row corresponds to this set. So that would be sulfur. How do we know that? Well, take a look at the ionization energies. Yes, they are increasing as we remove more and more electrons. But here you could see the big jump going from 8,500 to 27,000. We know that sulfur has 6 valence electrons, so seeing this big jump here at IE7, that tells us we are now removing a core electron, and all the previous electrons were valence electrons. So this, I feel, was very easy because of this division that's laid out here. That's between the valence electrons and core electrons. You might not see that every time. What you have to notice is the big jump going between the valence electrons and core electrons. Now let's test your understanding. A second row element has a large jump between its third and fourth ionization energies. What is the element? So press pause, Look at your periodic table to figure it out. And when you're ready for the answer, click play. Okay, so the answer here is boron. We're going to the second row. Here we go. So a large jump between the third and fourth ionization energies. Okay, so this is 1, 2, 3, and 4. This is where the large jump is. So that means the fourth one was really big. So we're removing a core electron here. All the other ones, from first to third, were valence electrons. So we were looking at boron, letter C. With our next question, based on what you just learned about ionization energies, explain why valence electrons are more important than core electrons in determining the reactivity and bonding in atoms. Again, pause the video, read through both statements very carefully, and when you're ready for the answer, click play. The answer is letter B. So we'll take a look at the second phrase here because that's the one that's different. Valence electrons are most important because they are held most loosely. That should make sense because with ionization energy, we are removing electrons in the valence shell. Yes, it's going to get harder and harder. We're going to need more and more energy to remove each successive electron. But once we hit the core electrons, that's where we're going to see a huge jump in energy that's needed. So those core electrons are held most tightly. Our next periodic trend is electron affinity, and that's where a neutral atom gains an electron in the gaseous state. So when that happens, energy is being released for the most part. So if a lot of energy is being released, then the more negative the value would be for electron affinity. So don't think that the number is getting smaller. It's just that it's becoming more negative. If you just take the magnitude of that number, then you'll see that electron affinity is getting larger. So be careful with the wording there. Now let's take a look at the trends in electron affinity. When you go down the column, the electron affinity decreases sometimes. When we move across the period, going from left to right, it becomes more negative sometimes. So the trends here for electron affinity, they're a little bit wishy-washy. But what you should know for sure is that halogens would have the highest electron affinity in any given period. Here you could see it's very hard to see any trend with electron affinity. Generally speaking, they are supposed to become more negative going from left to right. Okay, we could see that it jumps back and forth. What you should know for sure is that for any given period, the ones that have the largest electron affinity would be the halogens. Okay, they'd have the largest electron affinity, or in other words, the most negative electron affinity. The final trend deals with metals. So we're going to take a look at the properties of both metals and nonmetals. You should already know that metals are very malleable. So that means that they could be pounded into thin sheets. And they're also very ductile. So that means they could be pulled into very thin wires. They conduct heat and electricity. They form cations. We've been seeing that before. And they lose electrons in certain reactions. Or in other words, they would become oxidized. Nonmetals, just sort of think of the opposite. They're dull and non-reflective, whereas metals are very shiny. They form anions, and they also gain electrons, or in other words, they are reduced. So here's a mnemonic that you can use so that you don't get mixed up with oxidation and reduction. Oxidation involves loss of electrons. Reduction involves gain of electrons. Let's take a look at the trends now for metallic character. We'll see which ones are better conductors or more malleable. If you ever forget these trends, just take a look at the periodic table. The metals are on the left-hand side, nonmetals are on the right-hand side. So when we're moving from left to right across the period, the metallic character is going to decrease. When we go down the column, metallic character is going to increase. So here it's a little bit difficult, but just think of how easy it is to remove an electron from an atom that's very big. Again, think of atomic radius. If it's very easy to remove an electron from a metallic atom, then that means that that atom is a very good conductor, or that element is a very good conductor. You could add these to your periodic table with all your notes. Again, metallic character decreases going from left to right because metals are on the left-hand side. And metallic character increases going down a column. The explanation for the trends using the quantum mechanical model already mentioned in regards to going down the column. The valence electrons aren't held as strongly because they are so far away from the nucleus. And then going across the period, it's the same idea. Valence electrons are held more strongly because of the Z effective and the electron affinity. They increase going from left to right. So it's really hard for those electrons to be removed and move throughout the metal. Let's test your understanding. Which statement best explains why sodium commonly forms a 1+ ion and not a 2+ ion? So please pause the video, read these statements, pick your answer, and when you're ready, click play. The answer is letter C. It's the only one that's true. So sodium has only one valence electron. And when we try to remove a second electron, it's going to be much harder because it's a core electron. If you weren't too sure about letter C, look at letters A and B and see what's wrong with them. So for letter A, sodium only has one electron, so it only has one to lose. That is obviously wrong. Hydrogen is the one that has just one electron. Sodium has 11. Letter B, all metals form 1+ ions, and sodium is a metal. Again, not true, because we know for the elements in the second column, they form 2+ ions. And we've seen the transition metals, they could also form 2+ ions or even 3+ ions. Now use the periodic trends for metallic character to pick the one in each pair that is the more metallic element. So please pause the video, take a look at the periodic table to make your answer choices, and when you're ready for the answers, press play. Okay, so Sn is more metallic. Sn is more metallic. So we start here. And then we have to move to the right. Well, you see we are moving towards the non-metal section of the periodic table, moving from left to right, so Sn is the more metallic in the pair. Sb is more metallic than P. So we'll start off with P, and you can see that we have to move down the column. Electrons are being held more loosely in the valence shell. So electrons can be easily removed. That means Sb would be more metallic. Okay, so In is more metallic, so we'll start with Ge. We have to move down the column, so metallic character increases. And then we're moving to the left, with metallic character increasing more. Now with S and Br, starting off with S, we need to move to the right, so metallic character decreases. Then we have to move down the column where the metallic character increases. So because of the counter effects, we can't tell which one is more metallic. Even though both of these are non-metals, there is a gradient, if you want to say, in metallic character. Try out these 4 pairs now, again picking the more metallic element. So please pause the video, use the periodic table to figure out your answers, and when you're ready, click play. Now arrange these 4 elements in increasing metallic character. The last element that you're going to write would be the most metallic. So please pause the video, write down your arrangement, and when you're ready for the answer, click play. So here's a nice summary of the different periodic trends. If this visual works well for you, then please use it. I know a lot of students would rather have the periodic table in front of them and draw arrows and little notes in their own words so that they can understand the relationships, and not just the trends, but the relationships between the trends. So that's something that I highly suggest you use in understanding this part of the chapter.